Okay, this we will use the MATLAB to solve this problem, this general problem. Actually, it is the same as like the example that we discussed above, but we will do it again. Okay, we will use just only 2 elements. Okay, we use just only 2 elements, and this you may follow the step by text of Catran like this. For this problem, we define the node. This is node number 1, node number 2, node number 3, and this is node number 4. Okay, and we identify this element like the element number 1, and this is like the element number 2. Okay, after that, we identify the element number also. Element number 1, node I, node J, node M, counterclockwise, come back to element number 1. Okay, counterclockwise, node I is element number 1, right? For element number 1, this is node number 1, element number 1. Okay, counterclockwise, so this is node I, node J, and node M. Okay, so it means that node I for element number 1 is node number 1. Node J for element number 1 is node number 3. And node M for element number 1 is node number 4. Okay, this is very important. This is very important. For the step, you have to write this table is very important. This is very important. Okay, this table, element number 1, node I is node number 1. Node J is node number 3. Node M is node number 4. Okay, for element number 2, counterclockwise also. Node I is element number 1. Node J is element number 2. Node M element number 3. Okay, like this. Then the constant we define the constant E equal to 210 gigapascal. Okay, and the Poisson ratio for this case is 0.3. And after that, the thickness for this case is 0.25 meter. And the distributed load applied on the right hand side is equal to 3000 kilonewton per square meter. Okay, so we starting with the we have to open the MATLAB and select the correct workspace, correct folder that you store the file to that folder. Okay, so if you double click to that and the part is not in the same, you may set up set up the part first in order to change workspace that is compatible with the file. Okay, so I forgot how to set up the part. Okay, so I will skip it. Okay, I think you can find. I think it's maybe something. I have some. Okay, forgot it. Okay, this is the part already. Okay, we may starting with type the set up the constant, that is E, that is what? E6. Okay, this is the constant E, then mu is equal to 0.3. Okay, after that we set up thickness. Okay, it is the same thickness, so it is t equal to 0.025 for the problem. Okay, and then we determine the thickness K1. K1 is equal to what? Okay, use the commands of the element thickness. That is, should be like this. And change the value is E, new, and T already, okay? And then xi for element number one, is equal to what? Xi. Come back to the slide. Xi, we set up the coordinate over here, right? Set up the coordinate over here. For element number one, set up node I at the coordinate of the local coordinate. So xi for node I equal to 0. Yi for node I equal to 0 also. Then we move to xj is become 0.5. Yj is become 0.25. And then come back to xm is become 0. Ym is 0.25. Okay, so let's change the value to this 0. Oh, sorry. Then xj what? 0.5. Yj 0.25. xm 0. Ym is 0.25. Okay, and p is what? So this is the important thing to when you write the program, when you write the subroutine or something, the comment is very important. When you forgot something, we have to come back and read. Okay, so what p means on this case? P mean what? P equal to 1 for the case of plane stress, and P equal to 2 for the case of plane strain. For this case, we solve the plane stress problem. We have to use P equal to 1. Okay, we use P equal to 1 for plane stress. But if for the case that the problem of us is not plane stress problem, is plane strain, we have to use P equal to 2 instead, according to this M file. Okay, and you see the code. If you see the code, you see that if P equal to 1, metric D is become this. This is for plane stress. If P equal to 2, metric D is changed to be the plane strain problem. Okay. So after that, then enter. We only obtain the stiffness metric of element number 1. Okay. Do the same thing for element number 2. We can duplicate the command and do the same thing. Change it to be element number 2. Okay. For element number 2, xi element number 2. Okay. xi equal to 0, yi equal to 0, xj equal to 0.5, yj equal to 0, xm equal to 0.5, ym equal to 0.25. Okay. 0.5. This should be 0. Okay. And it should be 0.5 and 0.25 and 1. Okay. So what happened? So we obtain the element stiffness already. Okay. After that, we move to step 3. Step 3. Okay. Step 3 is assembling process. Okay. Assembling stiffness metric. We have to set up the stiffness first. Come back to the problem again. We have 4 nodes, right? Each node has 2 degree of freedom. So the overall degree of freedom, the total degree of freedom, it should be 8. So the stiffness side, the global stiffness side should be 8 by 8. So we set the stiffness side, capital K, equal to 0. Okay, and then use the assemble. Okay, use this M5. So the capital K is become the stiffness number 1 first. Node I for stiffness number 1 is node number 1 in global. Node J for element number 1 is node number 3 in global. And node M is node number 4 in global. After that, we obtain the global element stiffness for element number 1 already. Do the same thing for element number 2. Okay, do the same thing for element number 2. That is change to be K2. And it should be 1, 2, 3. Okay, so that's all. We have the global stiffness metric already. Then we will apply boundary condition. The boundary condition for this is what? The boundary condition is the displacement at node number 1 and node number 4 are equal to 0. Okay, so we have to eliminate the equation and solve it. Okay, according to this, we apply boundary condition. Then the boundary condition is u1x, u1y, u4x, u4y are equal to 0. And the applied force, applied nodal force, as we already determined, it is equal to 9.375 at node 2 and node 3 in x direction. And after we apply boundary condition, we will obtain this equation. Okay, so for the first one, we have to apply boundary condition first. That is the stiffness K, the small k, is equal to a part of the capital K. That is the row 3 to 6 and the column 3 to 6. Okay. Then we obtain the element stiffness after apply boundary condition, and then we will define the force vector. Force vector is 9.375. Okay, 0. 9.375. And then 0. Okay, we have the force vector already. After that, we solve for the displacement. Is equal to K backslash F. Okay, we have the solution. The displacement should be 0.7111. Okay, so if we compare with analytical solution, so you may compare it by yourself and you may have some comment. The comments is where we will discuss again next week when we meet together, and we will find out why the solution obtained from the finite element is something like this. Okay, so how can we solve the problem? How can we solve this problem? I think the solution is maybe not acceptable right now. Okay, it is not compatible with the analytical solution that we have learned in mechanics of material. Okay, but why it's happened like this? Okay, we will discuss again next week. Okay, and according to this, we solving the post-processing in order to find the reaction. We have to define the displacement, the total displacement first, and is equal to 0, 0 for node number 1, and U, and 0, and also 0 for the last node. Then we have this. And this is the nodal force vector for the global system. It is not this is not the reaction vector. This is not the reaction vector. It is the global nodal force vector that include the reaction also, but it's all is not reaction. So for this case, you see that the reaction is equal to minus 9.375. That is same as the applied force on the node, on the second node and third node. And also for the reaction in y direction, we have the reaction also, and it's balanced. It is in equilibrium, right? So the solution it should be okay. Okay. Then, if we would like to find the element stress, we have to know the nodal displacement. For the nodal displacement for each element, for the case of U1, U1 is equal to what? Is equal to U, the capital U, and node number 1. You have to write it in sequence also, in sequence of the node. And 6. Okay. Okay. We have the displacement like this. And then for U2 also, should be, and U4. is for Q2. Okay. So if you would like to find the stress, if we consider the code, what is it? It's determine what? It's determine the principal stress, just only
อาจารย์
principal
ครับอาจาร
stress.
ย์เขียนยูหนึ่งซ้ำกันครับอย่างเมื่อกี้
Okay, it's my fault. Thank you very much. Okay, should be all right. Okay. Then we will solve for the stress. Okay, if we consider the code, this code is determined for the principal stress. Okay, we require the stress before, so we have to use the M5 element stress first in order to determine the stress. Okay, in order to determine the stress from the displacement. That is determined from the stress is equal to dBu. Okay, sigma is equal to dBu. Okay, so we will use this M5, determine the stress first. The stress that is sigma 1. Okay. Okay, the stress in element number 1, we may define like that sigma 1. E mu, okay, and xi for element number 1 is 0. It should be 0. 0, so yj is 0.5. Sorry. Okay, it's correct. And then E for plane stress is 1. U is U1. Okay, then we obtain sigma, that is the stress. Stress occur in distributed in the element, and you see that it is uniform. It's not necessary to use shape function again because the stress is constant. Okay, over the area of the element. So in the same with the element number 2. For element number 2, sigma 2. Okay, and change a little bit. It should be 0. It should be 0. It should be 0.5. 0.25, 1 and 2. Okay. Then we have sigma 2 already. After that, if we would like to find the principal stress, you can solve it by yourself by using the we know that for Mohr circle, the principal stress is determined from the average stress plus radius and minus radius. Okay, the radius is determined from the square root of the value of the difference in normal stress over 2 square plus the shear stress square. Okay, so but we have the M file also, so we just use it. So for this case, we will use S1 to define the principal stress for element number 1. That it should be sigma 1. Okay, that's all. We obtain the principal stress already for element number 1. And for element number 2, okay, we obtain this. Okay, and I would like you to check the solution and discuss this solution again. What's happened to the solution that we obtained from the finite element? Okay, with the basic knowledge from mechanics of material, with this problem subject just only the uniaxial load. It is just like the tension force distribute over the uniform area. That is very easy to determine the stress distribute over the at any cross section. So we will discuss about this problem again next week. If you have no question,